Method of separation of variables or product method can be used to solve partial differential equation. Let's look at an example. Solve dou u by dou x minus 2 times dou u by dou y minus u equals 0 if it is given that u of x0 equals 6 times e raised to negative 3x. In this method, first step will be to assume that dependent variable u equals product of two functions x and y, where capital X is a function on independent variable x and capital Y is a function on independent variable y. We have u of xy equals x of x into y of y. When you partially differentiate this expression with respect to x on both sides, you get dou u by dou x equals y multiplied to dx by dx because y is treated as a constant. We have dx by dx can be written as x dash, and thus dou u by dou x equals yx dash. When you partially differentiate this expression on both sides with respect to y treating x as a constant, you get dou u by dou y equals x into dy by dy, which can also be written as xy dash. Thus you have dou u by dou y equals xy dash. When you give dou u by dou x equals yx dash in equation 1 and dou u by dou y equals xy dash in equation 1, also u equals x into y, equation 1 can be rewritten as x dash y minus 2xy dash minus xy equals 0. Here, this equation can also be written as x dash y equals x into 2y dash plus y. Now we do the variable separation. We have x dash by x equals 2y dash plus y upon y. This both equation can be equated to a constant k. When x dash by x is equated to k, we have x dash equals dx by dx. Thus, this equation can be rewritten as dx by dx into x equals k. When this dx is taken to the RHS along with k, this becomes dx by x equals k into dx. Similarly, when we have 2y dash plus y upon y equated to constant k, where y dash equals dy by dy, we have 2 times dy by dy plus y upon y equals k. When you multiply both numerators on LHS and RHS using dy, this equation becomes 2 dy plus y into dy upon y equals k into dy. This can also be written as dy by y equals k dy minus dy. This is because here 2 dy by y plus y dy by y equals k dy is obtained. Y and y get cancelled in the second term and we obtain 2 times dy by y plus dy equals k dy. When terms containing dy is brought to RHS, we have 2 times dy by y equals dy multiplied to k minus 1. Or it can be written as dy by y equals k minus 1 upon 2 into dy. Thus we obtained two equations involving constants k. When you integrate both this equation, we have integrating the first equation log capital X equals k into x plus log c, which can be written as x equals c1 e raised to kx. This is because when log c1 is brought to LHS, it becomes log x minus log c1. Since log a minus log b can be written as log of a by b, we have obtained in LHS log x by c1. Thus we have log x by c1 equals kx. When both sides of this equation are raised as powers of exponential function, we obtain e raised to log x by c1 equals e raised to kx, which becomes x by c1 equals e raised to kx. And we have x equals c1 e raised to kx obtained. Now integrating the second equation, we have log y equals k minus 1 by 2 into y plus log c2. Log c2 is brought to LHS and we have log y by c2 obtained. When you raise both sides as powers of exponential function, you get e raised to log y by c2 equals e raised to k minus 1 by 2 into y. Thus we have y equals c2 e raised to k minus 1 into y by 2. Having found the functions capital X and capital Y, we have u equals x into y and we obtain u equals c1 into c2 into e raised to kx into e raised to k minus 1 into y by 2. c1 into c2 can again be considered as another constant capital C, and this is the general solution. We have been given with the condition u of x0 equals 6 e raised to negative 3x, and we will apply that condition in the expression of u obtained as the general solution. U of x0 indicates that x is maintained as x and y should be given the value 0. Thus, we have u of x0 equals c into e raised to kx into e raised to 0. That is c into e raised to kx into 1. Applying this condition, we have c e raised to kx equals 6 times e raised to negative 3x. Constants can be equated and thus we obtain capital C equals 6. We can equate the powers of exponential function and thus we have k equals negative 3. Now we can rewrite the general solution giving the values capital C equals 6 and k equals negative 3. In this expression of general solution, we will rewrite c equals 6 and k equals negative 3. And thus we get the solution as u equals 6 times e raised to negative 3x into e raised to negative 2y, which can be written as 6 times e raised to negative 3x plus 2y, and this is the required solution for the partial differential equation.